Okay, so I'm going to take a grand perspective view of the whole universe, see the whole thing in one go, and let's say we have a blazar here that's a long way from Earth, black hole in the middle, spinning up magnetic field lines, and that accelerates jets of particles to relativistic speeds. Occasionally they'll knock against a photon in the galaxy that hosts the blazar and create a very, very high energy gamma ray. And that will toddle off through the billions and billions and billions and billions of kilometers of space until, just by chance, it hits the top of the Earth's atmosphere. And when it does so, let's say bangs into a nitrogen nucleus, and we get an electromagnetic pair cascade, and all these electrons and positrons shoot down through the Earth's atmosphere at the speed pretty close to the speed of light in a vacuum, but definitely faster than the speed of light in air. And so you get a pool of Cherenkov light comes out, and then on the surface of the Earth that illuminates a region maybe about 100 meters or so across. Now, what we have on the surface of the Earth is a couple of nice friendly astronomers here and here, say, and they have got a message from a friend of theirs who's a radio astronomer that there's an interesting black hole up here. So what they do is they build a couple of telescopes to try and detect the Cherenkov light coming from the gamma rays. Let's say there's one telescope here and then one telescope here. And these have got optical cameras at the top, and so when the Cherenkov flash comes down, these detect the Cherenkov light and they see, looking up, the electromagnetic pair shower as it enters the Earth's atmosphere. And if you look at the camera output from the two of these, so the astronomer on our left here might have a camera output that shows the electromagnetic pair cascade travelling like so, but this astronomer here on the right is looking at it from a slightly different angle. And so when you look at their camera, they might see it travelling down through the Earth's atmosphere at a slightly different angle. And it's the fact that you get these two different points of view pointing back up to the point where the gamma ray hit the top of the Earth's atmosphere, that gives you a much better handle on the exact direction that it came in from, and it lets you associate it much more clearly with whatever its origin was, like the blazar in this case. Right, now the catch is that these flashes don't last very long, and you can work out from the speed of light and the length of the air shower and the refractive index how long this little pool of light lasts on the ground. And that works out to be something like a few billionths of a second, which is an extremely short amount of time. Right, to give you a comparison, if you take a movie with your mobile phone, that takes pictures at a rate of 25 frames a second, whereas these cameras have got to take their images at rates of billions of frames a second. Right, so 40 million times faster than your phone. And this is where the very, very high technology starts to come in. So the physics we're dealing with now here, we've got our sort of beautiful black hole theoretical physics up in our target source that we're very, very interested in, but we also have to use extremely advanced physics in building the instrument itself to make the measurement. So we have detectors here at the front that have these photons that come in individually very, very, very fast, and you detect the little flash that lasts a billionth of a second, a few billionths of a second, and then you have extremely fast readout electronics, so you can take the data away and you can analyze all the images, and then you can do the combination between them and work out the different angles and get the information on what the astronomical source is up in the background. And so this is the CTA project, and the UK's involvement in this is to make about 35 telescopes worth of cameras and electronics to build a big array of these, which is going to be in the southern hemisphere in a few years' time. So the observatory site needs to be at a place where the Weather is usually very, very good and nice and calm, right? It's no good having a large amount of money spent on a telescope and then it's cloudy all the time. So they tend to be good sites in desert areas. You also need to be at a relatively high altitude so that the conditions are clear and clean in airflow. So you want somewhere where the airflow is coming in maybe off the sea, and you're at the top of a mountain next to it, so you're above the turbulent airflow. Then you want somewhere where you're definitely away from large centres of population, so that you don't have any light pollution coming in from street lamps and other sources. So when you're looking up at the night sky is itself as dark as possible. But even then, the night sky isn't completely dark. There's a small amount of light always coming in from the night sky. It's brighter when the moon's up than when the moon is down, so that in itself tends to limit your observation somewhat. You try to get you get your best observations, you get the darkest sky when the moon is down. But superimposed on the flashes that you get from the gamma rays is you'll always have a constant little background coming in from the night sky light and other particles that might be coming through that have been coming out from the solar wind and other sources of particles and cosmic rays going through the Milky Way galaxy. And that in itself then demands more sophisticated analysis techniques and the fast electronics as well, so that you're really sure that you're looking at just the signal that you see, and you can separate that from any background that's going to be coming in at the same time. And so construction of CTA is going to start in 2017 out at the observatory site, and at that stage then we'll start doing these things for real.